Gauss gun is an interesting physical device that uses magnetism and the transfer of momentum to propel a ball at high speeds. The Gauss gun consists of multiple repeating units, with each unit consisting of a neodymium magnet with at least one steel ball attached to it. Our setup is a multi-staged Gauss gun because each unit works together to propel the ball to faster and faster speeds. We can see that as the first ball starts to roll, it is pulled towards the first magnet. Then the next ball is released, which then moves to the next magnet. As each ball leaves in succession, this ultimately results in the final ball propelling with a velocity much greater than that of the first ball.
This is a section of the Gauss gun at full speed. When we push the first steel ball, it has an initial velocity, v initial. As it approaches the magnet, the ball accelerates. This acceleration occurs because the magnet is exerting a magnetic force on the ball. Thus we can say there is a net force on the ball, F net equals F mag equals ma. The ball continues to accelerate until it hits the magnet, at which point it has a final velocity, v final.
There are 3 balls of relevance in the first unit: ball 1, ball 2, and ball 3. When the impact of ball 1 occurs, the momentum of ball 1 is transferred to the magnet. Because the magnet is next to ball 2, momentum is transferred to ball 2. Similarly, since ball 3 is next to ball 2, momentum is transferred to ball 3. Ball 3 leaves with some velocity because there's nothing next to it. We can compare this to Newton's cradle, where only the balls at each end move while the balls between remain stationary. Now we know that momentum is transferred from ball 1 to ball 3, but how can we find the velocity of ball 3?
Because each unit is a closed system with no external forces acting upon the system, momentum must be conserved. In our non-ideal setup, however, there are non-conservative forces present, such as friction. Because these forces are minimal, we can neglect them and say that the momentum of ball 1 equals the momentum of ball 3. P1 equals P3, mv1 equals mv3, and therefore v1 equals v3, where v1 is the final velocity of ball 1. Therefore ball 3 has the same speed as ball 1's final velocity.
But why do we use 3 balls instead of 2? As with pool, it only takes the cue ball to hit another ball to get it moving, so why do we need one in between? The reason is that ball 2 is stuck to the magnet by magnetism. If ball 3 weren't next to ball 2 and ball 2 left with velocity v final, ball 2 would barely budge. By adding a third ball, we ensure that the velocity of ball 3 is the same, or nearly the same, as ball 1.
As ball 3 moves away from the magnet, it moves towards the second magnet. Thus ball 3 becomes ball 1, but for the second unit, with an initial velocity equal to v final. As it accelerates towards the second magnet, its velocity increases again. If we add more units, the final ball achieves higher speeds.
The kinetic energy of an object is defined as half its mass times the square of its velocity. As each magnet pulls on a ball, it adds kinetic energy to the ball. The speed goes up as the square root of the kinetic energy. This means that as we add more magnets, the speed goes up by a smaller amount each time. Therefore, the speed of the ball is a function of how many magnets we use. By increasing the number of magnets, the kinetic energy of the balls will continue to grow until the ball has enough kinetic energy to shatter the magnet.
Now let's analyze this phenomenon with actual numbers. Using Tracker, we can find the velocity of each ball. Let's analyze some footage of just one unit. After Tracker analysis, we obtain a distance versus time graph of ball 1. In the first section of the curve, the graph is essentially a line, meaning the change in distance per time or velocity for that section is constant, and there is no change in acceleration. According to Tracker, the velocity in this section is 0.143 meters per second. As the ball approaches more closely to the magnet, the speed of the ball suddenly increases due to the magnetic force. According to Tracker, the velocity the instant the ball hits the magnet is 0.267 meters per second.
To find the acceleration, we can use Tracker's plot fit to find an equation for the graph. This is the distance as a function of time equation as a cubic polynomial. Taking the second time derivative of this equation, we get the equation for acceleration. When the ball hits the magnet, t equals 0.867 seconds. Plugging this into the equation, we find that the magnitude of acceleration is equal to 0.155 meters per second squared. Let's find the magnetic force acted upon the ball. For this, we use the magnetic force is equal to ma, which gives us 0.0131 newtons. Now let's find the velocity of ball C. This will be the final velocity of the Gauss gun. According to Tracker, it is 1.13 meters per second. The change in kinetic energy therefore is delta K equals 1/2 m delta V squared, which gives us 0.0041 joules.
And this is how the Gauss gun works. Yay! Thanks for watching.